No one has come. कहाँ? Oh, 9. Some people are there. But I should be able to see, you know, how many are there.
Three people are there. 3 watching now. 3 watching now.
Oh. It's not only one. Hello everyone, good afternoon. Welcome to this live session of interpretative spectroscopy. If you have any questions right now, you can write it down so that I can start answering. To begin with, let me clarify some doubts you have about assignments. There were a couple of errors in the assignments. First, let me start with rhodium 1. I'm going to write it on the screen. Yeah. This question is about cyclotetraphosphazane. So we have something like this. So if you see, these two are substituted in a different way and these two are substituted in a different way. As a result, what happens, you can identify two types of phosphorus centers, and these two are identical and these two are identical. When you look into 31p NMR, these two will couple with these two to show triplet, and similarly this will show another triplet. So this is how the spectrum would look like. So if I say here this is PB, and if I mark this one as PA, so this is for PA and this is for PB. If you do not understand this one, you just recall, okay, these two are identical, and when these two are identical, they are interacting with this one, two are there, you use simple 2ni plus 1 rule. Okay, 2ni plus 1 rule, 2 into 2 identical phosphorus are there and spin is half. 31p, you should remember, it is 100% abundant, and I equals nuclear spin I equals half, okay, plus 1, so it gives 3 lines. So you can see 3 lines is there, 1:2:1, and then similarly other one also, this for, if you consider this for PA, same thing holds good for PB as well. 2ni plus 1 equals 3. 1:2:1. Okay. I hope it's clear for you people. Any question about this one? Please write on that chart so that I can further clarify your doubts in case if you have any doubts about this problem. So if you say okay, then I would proceed further. Otherwise, I would wait for a couple of minutes to hear from you people. One of you should write okay or something like that so that I can proceed. If someone hasn't understood, you can also write so that I can come back again and explain. It's very slow. It does not come. Oh. It has come.
Yeah, it has come.
Very slow. Is it okay? Who asked this question? Mahesh. Yes, sir. Whether he's there? I used to see yesterday.
Mr. Mahesh.
Mahesh, is it clear for you now? Are you attending?
Give one more example.
Can you check Mahesh is there?
Rupali is there. Give one more example, she said. Rupali, give one more example.
So you want one more example? No issues. Okay, I will take another example. Similar example I will take. Let me write cyclotriphosphamine. If you look at this example, we have 3 phosphorus atoms are there, and this is called cyclotriphosphamine. So this phosphorus has 2 methyl groups, and this phosphorus has 2 methyl groups, whereas this phosphorus has 2 phenyl groups. So these two are identical. For example, if you try to rotate like this, if you do C2 symmetry operation rotation, these two cannot be distinguished, so undistinguishable. So these two are identical. Let's say these two are A, and this, let me call it this as X or something. Then this is a to X type spin system. Now this one would couple with these two equally, and this is 2, number is 2. So then if you use, this is for Px. So 3 lines will be there. And now these two would be coupling with this one, only one is there. If you take 2Ni plus 1, you will get only 1. Now this is for Px. Now this is for Pa. What you get is a doublet. This is 1:1, and this is 1:2:1. And if you are curious how this 1:2:1 is coming, okay, for example, when you place this one in the magnetic field, small magnetic field generated due to this nuclei, Pa to Pa, they also interact with the applied magnetic field, and they can align with the magnetic field or they can oppose the magnetic field. In that case, what happens? You have several possibilities. So let's take 2, 3 are there. Let me write like this. 1, okay, both are upward, and then you have one upward, one downward, and this can be one downward, one upward. So this is something like this, and then both of them can be downward. Now these two are degenerate. Now this is 1, this is 2, and this is 1. This is how you get 1:2:1. Is it clear?
Mahesh says he got it.
Oh, okay. Yeah. Hope it's clear now. You want one more example? What's her name?
Rupali.
Dipali.
Rupali.
Rupali, is it clear for you?
Yeah, so the forum queries, these are the ones.
Yeah. This is how to go to next page. Okay, got it. Okay, so now let me clarify your doubts about other questions. Okay, we're talking about, there is one question. This we have given all the structure, right?
Yes.
Okay. So this compound we have already given. This is very similar to Wilkinson catalyst. What we have is a square planar complex. Of course, if you do electron count, this is a rhodium 1 system. This is 16 electron system. Okay. So 8 plus 6 plus 2. 16 electron system. It's a square planar complex. If you just look into it, 2 cyclophosphine, tricyclophosphenes are trans to each other, and one is cis to both of them. Okay, one is trans to bromine, other are cis to bromine. And if I try to use this axis and do rotation, these two are identical, so I can call them A, and then this is, I would call X, and now M is also NMR active. We have a AMX system. So now we are asking about rhodium NMR. Okay, there was a mistake, I think. The question asked is about 103 rhodium NMR. Okay, it is given as 31P 1H NMR. Even that also I can explain. It's not a problem, so that you will be knowing little more. So if you consider 103 rhodium NMR, what you should do is rhodium 103 rhodium is 100% abundant, and I equals half. Okay. So now if you consider this rhodium will be coupled with these two, A, in a different way compared to the one, this is trans to bromine. First, always trans coupling will be more. So what happens is rhodium first couples with these two, and again here two are there. You know that 2Ni plus 1 rule you can use, and first what you get is you get a triplet here, something like this. Okay, so you get a triplet. Rhodium is, this is your rhodium phosphorus coupling, PA coupling. Okay, now this will be further split into doublet by this one. This, whatever is there, the space between these two lines, this is called rhodium PB coupling. Okay, all are 1J coupling. Okay. So now I have to sketch the spectrum now, and you should remember this is 1:2:1. This intensity should be retained here. Now the spectrum should look like this. This is 103 rhodium NMR spectrum. So this includes both 1J rhodium phosphorus A coupling and also 1J rhodium phosphorus PB coupling. Is that clear? So now I shall explain 31P NMR spectrum also. This is a little bit more complicated. Nevertheless, you can understand now. Is it clear? Once you say yes, I will go further. Mahesh and Rupali. Any else is there? Any else is there? Only those two.
Seven people are. 7 people are.
Okay. Yeah. Okay, now what I will do is I will try to explain 31P NMR spectrum for this molecule. Let me write here again the structure. Remember, this is a square planar complex. Now if you consider again 31P NMR, of course when we are taking 31P NMR we are decoupling with proton. We should write like this. Now we have to consider two factors. This phosphorus, these two will couple first with rhodium and then it will couple with phosphorus. Similarly this one will first couple with rhodium and then this will couple with two phosphorus atoms. Let us consider first for this PB, simple one. First it will be split into doublet and this one is 1J rhodium PB coupling. Okay. So now each line will be split by PA. So this will be now triplet. This coupling, this space all are identical. This is called 2J PA PB coupling. Okay. So whether I consider PA PB coupling with this one or PA, they are identical. So now I have to sketch this one again 1:2:1 and then this is 1:1. So while sketching it should be something like this. Okay, this is for PB. Now we will go for PA. PA also same way, these two will couple first with rhodium. There may be a little bit change in the magnitude of rhodium to phosphorus coupling. So now only one is there, each one will be split into doublet. Okay, because of this PB here. 1:1, 1:1. So this is this space, whatever is there, is called 2J PA PB. You remember this, whatever the space I have given here, and this is same as this space here. So now I have to sketch this spectrum. Okay, see how the 31P NMR spectrum would look like. Okay. Yeah. Is it clear, Mahesh? Good. Okay. You have any other question? Okay. I would go ahead about 207 lead example here. So we are talking about tetraethyl lead. Actually here question asked is about 1H NMR. Okay, it is about 1H NMR, it was a mistake. We are talking about 1H NMR. The option given also corresponds to 1H NMR here. So when you are considering 1H NMR, it's not 1H NMR. Tetramethyl. Okay. This is tetramethyl lead. This is a tetrahedral molecule. When you look into lead isotopes, we come across 4 isotopes: 204 Pb, 206 Pb, 208 Pb, and 207 Pb. So we have totally 4 isotopes are there. This is about 1.5%, and this is 52%, and this one is 206 is 24%, and this is 22%. Okay, approximately, and all are I equals 0 here, you should remember. And this is I equals half. So that means basically we should focus our attention about this. Collectively it becomes 78%, and this is 22%, and this 22% is NMR active. For example, if I take 100 molecules of tetramethyl lead, out of that one, 22 molecules will be having 207 Pb isotope with I equals half. Remaining 78% will be having I equals 0 isotopes. It doesn't matter whether you consider 204, 206, or all are identical. We have 78% nuclear NMR inactive isotope. So in that case, what happens when you look into 1H NMR? So 1H NMR would interact with 0. In this case, there is no coupling. You get one line here. So this accounts for 78% of lead with I equals 0. That includes all these 3 components: this one, and this one. Okay. Now remaining 22 is there. This 22, what happens? This will couple with this hydrogen to doublet. Again, this is 1. Now you go with simple 2Ni plus 1 rule here. Okay, 2 into 1 lead is there, and its spin is half, so it becomes 2. So this one would appear something like this here. Okay, this, whatever this spacing is, this is called 2J, I think. Yeah, this is called 2J Pb 207 H coupling. Okay, so now this is how the spectrum would look like. I think 4 spectra are given. You should be able to distinguish. This is 78%, and then if you look into the intensity, this will correspond to 11%, and this correspond to 11%. Okay. Similarly, I have explained 195 platinum NMR also, in which we have 34% NMR active platinum nuclei with I equals half, and remaining 66 is I equals 0. Same thing happens if you consider 100 molecules of platinum complex, out of which 34 will be NMR active and 66 will be NMR inactive. Similarly, if you take selenium also. Is it clear now? So let me move on to mercury complex now. Is it clear? Shall I move on to the next one? Why others are silent? Rupali, Dr. Mahesh. It has come, right?
Yes, sir, it's coming.
Okay, so it has synchronized now, right?
Yeah. They are coming and going.
Okay, next, let me move on to the next problem here. question is about
This one was the
mercury enema.
Yeah, mercury enema. That's a long range
What is
coupling.
mercury? Mercury is about?
So
So here the question is about mercury NMR
199.
199. This is about mercury 199. Okay, so here I equals half, and its abundance doesn't matter because worried about only looking into mercury NMR. So we'll be actually looking into only those nuclei which are NMR active. So when you look into this one, now we have to see what are the other nuclei to which it can couple. Now we have fluorine is there. Of course, fluorine 19F, I equals half, and it is 100% abundant. And I have to identify now how many, this is one type, and this is another type, and then another one is there, this C. Okay, so there are three types of fluorine atoms are there. The first one, 1, 2, so 2 bond apart. First what would happen is this will be coupled with, mercury is coupled with this one to give a triplet, that is with Fa. So something like this, it will first, this is, you can designate as Fa mercury coupling. So now next one is 1, 2, 3. Okay, so now 3 bond coupling is there with Pb. So again this is further split into triplet. So this is not up to the scale, so all are identical. So one I am writing here, this is 3J mercury Fb coupling. Now what is left is this one. So this is essentially C. So 1, 2, 3, 4 bond coupling now. This 4 bond coupling is also can be seen in case of mercury. So this is, if you put, what happened? Control. It doesn't come, right? Yeah, it's over. Okay, so now this is 100% abundant. So these are Fc here. Okay, so now if this I have shown, now we have 6 equivalent ones are there. If 6 equivalent ones are there, how you will use again 2ni plus 1 rule. Okay, 2 into, there are 6 of them are there. 1, 2, 3 here, 1, 2, 3 here. 1, 2, 3, 4, 5, 6. Okay, I have 6 I have written here. Plus half into half, it gives 7 lines. Okay, so now 7 lines, each one will be split into so something like this, each one will be. So it goes like this, all of them will be, it's very interesting to sketch this one. This is 1:2:1, and this is 1:2:1, 1:2:1, 1:2:1. So now this will be, of course, you can calculate 7, what is the intensity ratio using Pascal triangle. So it would appear something like this. Okay. So it goes like this. Okay, so you have 3 sets here, and again here you have longer ones, because this 1:2:1 ratio should be, and of course the exact spectrum I have given in my lecture, you can see that Okay, this is how you can see a triplet of septates is what the spectrum looks like in this case. Is that clear?
Yes, exactly, got it.
Okay, yeah. Any other question?
So it's one is girl, but she's not online.
Hmm. No,
And you
then
can
leave it.
explain the
Yeah.
terms in
Okay. Oh, there was one more. Okay, probably this D2 system, while writing term symbol, there was a mistake. Okay. Of course, you all know how to write term symbols and also finding out the values. If you take this is plus 2, plus 1, 0, minus 1, minus 2. Two electrons are there here. If two electrons are there, L equals 3. L equals 0, 3 means you can here 0, 1, 2, 3, 4, 5 L values we have S, P, D, F, G, H. It goes like this. Now we have to choose here 3, so we have to go for F. So F we know the term now. And then here what we have is, of course you should remember L 2s plus 1, here J is L plus or minus S. So this is how we write term symbol, and 2s plus 1 will be here 3. 2s plus 1 will be 3. Okay, so now this is less than half filled, then it should be L minus S. So L minus S means L is 3, S equals 1. So L minus S equals 2. So here it is 3F2. Okay. So this is the correct one, not 3F0 is wrong. Is that clear? Yes. So if you ask me what would happen if it is half filled, then you get again, they will cancel out. Okay, L will be 0. Okay, and then of course yes, it may not be 0, then it becomes J equals L. J equals S it becomes. When it is half filled, your value will be L equals 0 it becomes. Okay, 3 cancels. So in that case, what would happen? Only have to count, this will be 2.5. Okay, J will be, in case of this one, if you have D5 system, your J will be just L minus L plus or minus S, whatever you take, this is 0, and then you take a positive value, this will be 2.5, will be the S value. Okay. Is it clear?
Yes, right.
Yeah. Okay. Any other questions you have? So whatever the doubts that were posed through mail, I have clarified now. If you have any more questions that needs to be answered, please go ahead and write on the chat box so that I can answer. So how is it course? You people are enjoying it? So you have more interesting problems are there. At the end, there are more than 55 problems are there covering all spectroscopic aspects, NMR, UV visible, IR, mass and mass bar. Any questions, Dharav? Rupali is silent now. So if you have some questions, I shall answer, otherwise I have to wind it up. Tell me. I will give you 2 more minutes. Okay. Okay. Oh, okay, let me explain about, I will consider again this styrene. Let me change the pen coloring, maybe getting bored with red color now. Okay, let me take this one now. Okay, we have 3 hydrogen atoms. I have denoted them in 3 different colors now. Let me call this one as A, B and C. If you just see here, the relationship between HA with HB is different from relationship with HA to HC. Similarly, HB is differently interacting with HA and HC, and B and C are on the same carbon atom. Okay, and if you just see here, they do not have any way with any simple rotational operation. You cannot make them indistinguishable or something like that. So in this case, what happens? Strictly speaking, they are all chemically and magnetically non-equivalent. These HA, HB and HC are chemically and magnetically non-equivalent. Well, I would say chemically they are equivalent. Okay, these two are chemically equivalent. This is, but these two, what I am telling about B and C, let me say anyway, these two are chemically non-equivalent. So these two, if you consider B and C, HB and HC are chemically equivalent, but magnetically non-equivalent. Okay. As a result, what would happen? You will see geminal coupling. Okay. And then in a higher magnetic field, what would happen? The separation in halves will be much larger compared to the coupling constant. As a result, it appears like AMX system, and each one will show a doublet of doublet. That's what I have shown in my lecture. Okay. So now if you consider HA would couple with HC first. trans coupling is more, and then this will be coupling with HB, so you will get a doublet of doublet. And similarly HB will be coupling with HA first, and then this will couple with this. This always geminal coupling will be much smaller. Well, what you get is, so something like this, and then HC also same thing. HC will couple with this one, and then it will couple with HC. So you can get the spectrum like this. Okay. And if you take a smaller field strength like 60 megahertz or 100 megahertz, what would happen here? The chemical shift difference will be much smaller than the coupling constant. In this case, you will see second order spectrum. In second order spectrum, you will be seeing in a different way. But when you increase the field strength, magnetic field strength, then the peaks will be well separated. In that case, it would appear like first order spectrum. So otherwise there is a possibility of merging of those things. I have shown already with a series of spectrum how one can change AB to A2B2 or ABC and AMX and all those things. Just go through that one, you will get the answer. Okay, is it clear now?
Two more questions. They are asking when to consider the 4-in-1 coupling. I think that is for mercury case.
Well, unless there is a see, for example, if fluorine is given in that example, you should anticipate that the intention is to find out. Doesn't matter, it may be a smaller in magnitude. Okay, there are examples where we can see up to 6 bond coupling. Okay, I myself have seen in our research up to 7 bond coupling. So as long as some NMR active nuclei are there, there is no harm in showing the larger coupling also. But when you actually look into the spectrum, many times you may or may not see those large range couplings. But in this case, mercury I have shown 4 bond. It more or less you can see up to 4 bond, you can see 5 bond you can ignore. Up to 4 bonds, if any NMR active nuclei are there, you better to show, okay, that long range coupling as well. Yeah.
Question is, they are asking with this example why we are getting doublet of couplet in this one.
For
Phosphorus.
okay. Yes, I would come to that one. Okay, that example, I'm going to write it. Okay, we are taking 1H NMR, right? Yeah, this we are taking 1H NMR. Okay, so you take something like this. If you just look into the molecule, see this P is bonded to 2 oxygen atoms, whereas this phosphorus is bonded to 2 carbon atoms. So they are both chemically and magnetically non-equivalent. So when you look into 1H NMR, okay, so first let us say, if you see here, let me write in a better way, so that you will get some idea about how many bond apart they are. If you see, of course, CH2, CH2, CH2 are there. If you just see here, 1, 2 bond, and here it is 1, 2, 3 bond coupling. So first what would happen is they will be coupled with this phosphorus because they are only 2 bond coupling. Then it will show a doublet, and then this each line will be showing further doublet because of this one. This coupling you should note it as 2J P X H. Okay, now another one will be, this is 1, 2, 3. also the spectrum would look like something like this. Okay. So this coupling is P, okay, PH coupling, PAH, and then this gap is 2J PX H coupling. Okay, is it clear now? Why it shows doublet of doublet? Hmm. Yeah, well, yes. Here the convention is very different in case of nuclear spin. Plus half is stable, lowest energy, and minus is highest energy. Whereas in case of electronic, we go for a different notation. Okay, that's the reason we are considering here. Whatever the plus values are, they are lower energy, and minus are higher energy in case of nuclear spin. And also nuclear spin selection rule, you should remember delta S equals plus or minus 1, whereas in case of electronic, it's delta S equals 0. Okay, so electron, when electron is there, when it is excited, it should go like this only. Okay, it should not go like this. This is spin formidable. Whereas in case of nuclear spin, since delta S equals plus or minus 1, so nuclear spin, this one become this one here when it goes to excited state. Is that clear? So what is your comments about this course? Is it easy to understand? Is it beneficial for you people? So give me the feedback. Rupali, Mahesh, and then Dharav. Oh. Shashikala, you joined just now? Hmm. I think Shashikala is teaching in a college, I believe. Okay. Yeah, at the end you have many more interesting problems are there. I hope you enjoy it. Okay, and also they are ideal for teaching us in case if you have taken teaching as your profession. Well, why did you join so late, Shashikala? So I explained many things in the last 50 minutes. Anyway, this YouTube is available. Probably you go through it, and then if you have still doubt, next time you please join on time and come up with some problems that you face, or if you are teaching your students face, certainly I would try to clarify those doubts so that you can do a good job. Okay? Okay, another few minutes are there. You have any doubts, Sasikala? Yeah. It's not possible. Okay, so what you do is you accumulate all the doubts you have, okay, Rupali, and you come up with all those things in advance so that I can deal with some of them. Whatever the doubts you have, no matter how many doubts you have, doesn't matter. You just post all those things, I will keep all those things, and then in another live session where you promptly joined in time, so I shall get those things clarified. Okay, and yeah, as you know that this is available online, please go through it, and then next time please join. Okay. Well, all those things I have already showed. You please go through it, and if still there is a problem, please join. I will explain at least 2 to 3 problems for problems for you. Okay. I just now explained everything. And if you have questions also, you can also write to me. No problem. I shall try to answer it. But certainly, in my next live session, I would, take up more problems to solve your problems. Okay, then see you in my next session. Until then, have an excellent time. Okay, and wait for next series of lectures coming in. Will be opened in the next few weeks. Another 3 weeks are left, right? So another 3 weeks are left. Okay, another 15 lectures are waiting for you people. Very interesting ones. Hope to see you all in my next live session. Yeah.